Hello, and welcome to Strategic Energy Group's short videos presentation on diagnosing leaky valves. So let me first define what I mean by leak by, because I'm going to be using that expression frequently. Simply put, it's a term used when a fluid or a gas such as steam is moving through a valve when it shouldn't be. If the valve doesn't seat properly, the fluid can push past the valve seat and through the valve. Here we have two different types of valves, normally open valve and a normally closed valve. Also, let me define the term actuator as it pertains to valves. The actuator is a device that attaches to a valve and responds to a control signal by mechanically operating the valve to open or close and control the flow of water or steam through it. Normally open valves are valves that fail into the open position, such as the heating valve in our previous example, and are usually held open by a spring within the actuator. Since the valve's actuator must continually overcome the ever-present opening force of the spring, normally open valves are more susceptible to leak by, since the actuator and the control signal are responsible for holding the valve firmly shut. Just a little drift in calibration of the control signal can allow the valve plug to lift off the seat and allow leak by. On the other hand, the normally closed valves use an actuator with an internal spring designed to keep them shut without needing the actuator to work to hold the valve firmly seated. Chilled water valves are usually normally closed type of valves. They're dependent on the control signal and the actuator to drive them open when cooling is needed. Without a control signal, or if the actuator fails, the valve remains in the closed position. Valve actuators, as well as their control signal transducers, will drift out of calibration and allow leak by, such as with DDC systems. Any drift in the voltage output to an electric actuator can potentially allow leakage. And then with pneumatic actuators, their diaphragms can develop small leaks and still function, but they may no longer be able to pinch off the flow completely. Also, their pneumatic controllers need to be checked and calibrated annually, as they will tend to drift out of calibration. Then in DDC to pneumatic hybrid systems, the DDC's electrode to pneumatic transducers are notorious for drifting and needing frequent calibration. So whether it's by means of pneumatic or electric control, the span of the control signal to the actuator is critical. It needs to be specifically set up for each individual valve, because manufacturing tolerances can affect the actual operating range. Just because it has a specified spring range or voltage range doesn't mean it will open fully or completely close with exactly those values listed for it. Also, if the control signal span is adjusted too tightly around the valve's operating range, there will be no leeway for any drift in calibration that will eventually happen over time. For general HVAC, it's best to have a slight bit of overspan in the control signal. For electric DDC actuators, you want about 1/2 to a full volt of overlap above and below the span of the voltage that's needed to drive the valve between fully open and fully closed. Then for pneumatic systems, since most pneumatic controls are getting pretty old and sloppy these days, I recommend at least 1 full PSI of overlap as being even better to help prevent leak by. And then you also need to realize that excessive system water pressure can lift valves off their seats. This can be caused by something as simple as an improper pressure set point adjustment for the pumping systems, or out of calibration pressure transducers that send the pressure feedback signal to the controls. Then foreign material, such as pipe scale, can get lodged under a valve seat, preventing it from sealing off completely, as well as possibly damaging it. So damaged valve seats are another cause. A form of valve seat damage called wire drawing causes a lot of persistent valve leakage issues. It's essentially an erosion or pitting of the valve seat, which makes it impossible to seal off all flow. This type of valve damage can be caused by valves that spend a lot of time nearly shut but not completely shut, as the constant pressure drop across the valve will allow high velocity fluid to actually cut into the valve seat. So valve control signals that are not kept properly adjusted to fully seat and shut off all flow can uh, allow continual leak by and eventually eroding and permanently damaging the valve seats. Then of note in this picture is a device called a pilot positioner. And I can see that it's been disconnected from the valve and abandoned in place, which can be problematic. With less and less pneumatic control experts available these days, people are looking for ways to reduce their number of pneumatic devices whenever possible. And while pilot positioners are an additional device that also needs to be kept calibrated, they shouldn't be removed from the system without careful consideration, as they provide two very important functions. First is to allow the ability to functionally shift the spring range of a valve, such as if two valves with the same spring range are to be operated in a sequential manner. For example, these two valves in the picture appear designed to operate as what's called a 1/3, 2/3 steam valve arrangement. The smaller sized 1/3 valve provides for good modulation control at the lower loads, while the larger size 2/3 valve provides higher volume and better control under higher system loads. The pilot positioner is used to shift the spring range of the larger valve, so it opens only after the 1/3 valve has fully stroked open. Here, though, the pilot has been abandoned and the control signal is now split to feed the two valves exactly the same signal. In a steam system, this can make it very hard to achieve good control when under light loads, as this system will likely end up hunting and cycling excessively, and ultimately prematurely wearing and damaging the valve seats. Then a pilot positioner's second important function is to provide a higher volume air signal that many controllers are not designed to provide. This comes invaluable when operating larger valves with larger diaphragms. Using a pilot positioner can provide faster modulating action. And even more importantly to this discussion, they provide better ability to pinch off high pressure systems, as the larger size valve diaphragm will have mechanically greater closing force. And without the high volume capability of the pilot, the system will be slow to react, and particularly slow to react to any leakage that can be happening. So what's a good way to diagnose a leaky valve? Well, that depends on what type it is. Here we have a simple two-way valve. Notice the infrared thermal image is showing high heat on the supply side of the valve, and then notice how there's less heat on the discharge side of the valve. But there's still a significant amount of heat on the discharge side. So the question is that heat caused by leak by? Or could it be merely residual heat left from the last time the valve modulated? Then again, it might also simply be thermal heat conducting down the pipe. So an IR imaging scan such as this of a valve body doesn't really help us determine if the valve is leaking by. But since this is a two-way valve, an ultrasonic listening tool can reveal the sound of water as it passes through the seat, which allows us to quickly determine if there's water hissing as it passes across the valve. Of course, you need to be certain that the valve is actually overridden shut when you are checking it, as the controls otherwise would still automatically be able to stroke that valve partially open if it wanted to. Two-way valves with straight through flow are pretty easy to figure out what they're supposed to be doing. If the valve is completely shut, the valve should essentially be silent. But if there's leakage, then turbulence will be formed as the steam or water squeezes past the valve seat. An ultrasonic listening tool does a great job of enunciating that noise generated by the turbulence. Using an ultrasonic listening tool with a metal probe allows you to touch at various points around the valve, and you can easily narrow down where the sound is emanating from. Is it coming predominantly from the bottom of the valve, which likely indicates leakage past the valve seat? Or does it get louder as you move away from the valve, which likely indicates residual system noise telegraphing down the pipe, and probably not a leaky valve. But with three-way valves, these can be more complicated to diagnose for leak by. As opposed to the easy to understand two-way valve, three-way valves bring another path of flow into the picture, and they can be either a diverting valve or a mixing valve. Here we have a diverting valve used to divert a single input stream through either of two outlet ports. And then here we have a mixing valve, which is used to mix two input streams into a single output. Nevertheless, with either type, three-way valves are much harder to diagnose since they're always flowing water through them anytime the pumps are running. So ultrasonic won't tell you if it's leaking by because it's always going to be noisy. And we saw a couple slides back, trying to diagnose leakage across a valve body using infrared just doesn't work very well either. So for diagnosing three-way valves, it's best to measure for leakage right at the heating or cooling coils that are being controlled, and then overriding the valve shut and measuring for any residual heat that still may be entering the coil. Best practices used to avoid problems with leaky valves should include surveying for leaky valves annually. This is especially important if boilers and mechanical cooling are allowed to operate at the same time, as a leaky heating valve is oftentimes masked simply by the cooling valve right after it in an air handler. It will automatically just open up wider to overcome the heat that's being imparted into it from the leaky valve. And then two, develop and use a standard operating procedure for each type of valve to make sure it's surveyed correctly each time. And then three, be sure to schedule it into your PM system so it doesn't get overlooked and forgotten. For two-way valves, using ultrasonic listening tool is a nice and quick way to check them. But for three-way valves, you'll need to check for leak by at the coil that it's controlling. And there you're going to want to measure the delta T across the coil. It's a good way to check. Using a temperature probe, you're going to want to measure for any difference in air temperature entering the front of the coil to the difference of the temperature exiting the backside of the coil. For heating valves, you're going to be looking for a temperature rise from the inlet side to the outlet side of the coil. Ideally, there should be at least should be less than 1/2 degree difference. It's best to take a couple of measurements and average them. And then there's a quicker and easier method, though, for both two-way and three-way valves, if you happen to have access doors in your air handlers that allow you easy access to the face of the coils. Then using an IR imaging camera, you can simply scan the face of the coil for any differences in temperature across the face of the coil. This can be one of the best ways to reveal if the valve is leaking by, such as in this picture, where we see residual heat still entering the coil. With the valve commanded shut, and after waiting at least 30 minutes, we would have expected to see the whole face of the coil approximately the same color, meaning about the same temperature. And then don't forget to check these other types of valves, chill water valves. And here again, you'll need to command the valve shut and wait for the coils to reach equilibrium with the airflow, and then measure the delta T across the coil. For cooling coils, you're going to be looking for a temperature drop from the inlet side of the coil to the outlet side of the coil. And true here is if you do happen to have access doors, IR imaging can be a really good way, quick way too, to check for any residual differences in the temperature across the face of the coil. And then don't forget about reheat valves out of the terminal boxes. Again, you should command the valve shut and wait at least 30 minutes. For DDC systems, you may actually be able to use a global override and command multiple reheat valves closed with a single command. If so, try to do it for a whole floor. That'll allow you to go out and quickly survey the whole floor and all the ceiling supply grills, scanning them with, say, an IR temperature gun, and look for ones that are unusually warm. That could indicate you've got a leaky valve there on that reheat system. And then finally, when checking and calibrating the span that's needed to properly drive the valves, Be sure to always use the same instrument each time, as different instruments will rarely read exactly the same and could induce error into your calibrations. And then, of course, measuring instrument that you're going to be using for calibration should be kept well calibrated itself. And this is especially true for pneumatic gauges, as they tend to be fairly inaccurate at pressures below 5 psi. And many pneumatic valves have spring ranges starting at only 3 to 4 psi. So just a half psi too much pressure may end up lifting a normally closed valve off its seat. This concludes our presentation today, and I hope that you found it enlightening and understand the importance of checking your systems for leak by. So thank you for attending.